There you go. Good day, everyone. Thank you for joining us for day 2 of CosmoPalooza. So for this first session, we're very happy to give a platform for an update from Euclid. I see a raised hand. I would suggest that instead you pop up your question either in the chat or in the Q&A, and we'll address it right away. So yes, for Euclid, we're very happy to welcome Peter Taylor, who's going to give us that update. While he's giving his talk, we encourage you to use the Q&A feature to submit your questions. They will be answered live at the end of the talk, and we'll preserve the answers and the questions that we'll put in a separate document that's going to be available from the website. So even if you need to run out during the talk, then you can be sure that your question will be answered. So now, without further ado, Peter, you're welcome to take over.
Can you enable screen share? Video.
Oh, okay. Asked to turn on video. That should work now. Sorry about that.
Okay. Okay, can see the slides?
Yes, very well.
Okay. Perfect. So I'm Peter Taylor. I'm a postdoc at Ohio State. And today I'm going to be giving you a Euclid overview, both about the instrument and the science as well. So I think Euclid's just going to be an incredibly impressive cosmology experiment in its own right. But I also did want to emphasize some of the possible cross-correlations that we can do with some of the other experiments that are going to be discussed this week. Okay, so what is Euclid? It's a European Space Agency M-class mission, so mid-class mission with NASA contributions. It has a 1.2 meter primary mirror, so roughly speaking, about half the size of Hubble. But unlike Hubble, it's a survey instrument. And we're going to conduct both a photometric and spectroscopic survey over effectively the entire extragalactic sky. The primary science goal is to understand the nature of the accelerating universe. And to do this, we're going to use a combination of weak lensing and galaxy clustering. So both photometric and spectroscopic clustering as well. But it really is important to emphasize that in the Euclid Consortium, which ESA has tasked with analyzing the data from Euclid, we have a large number of other working groups focusing both on cosmology and astrophysics more broadly as well. And the Euclid dataset will be made public, and it will serve as a really important legacy data set for both cosmology and astrophysics more broadly. Okay, so Euclid blasted off on the 1st of July this year on board a Falcon 9 rocket from Cape Canaveral in Florida. So I was lucky enough to brave the kind of insane temperatures and humidity, and I guess more importantly, the giant insects flying around Florida in the summer to go and watch the launch. I've been in Euclid now for 7 years, so I found it really stressful. I wanted everything to go right, but fortunately it did. So here is Euclid detaching from the launch vehicle about 40 minutes after launch. It's already going at a speed of 27,000 kilometers an hour at this stage on its way to L2. And then this is the last image that we have of Euclid. Okay, the video doesn't play, but if it did, you'd see Euclid streaking across from the top to the bottom of this image 11 days after launch, and that was captured by the CFHT megacam. So Euclid is now safely at L2, collecting data inside its science verification and commissioning phase, and we're expecting to start the main survey later this year. Okay, so what about the instrument itself? So this is what Euclid looks like. Here it is in the clean room just before being loaded into the launch vehicle. Just to give you a kind of sense of scale, this is 3 meters at the bottom and about 4.5 meters high. So roughly speaking, it's the same height as a fully grown female giraffe. and Euclid weighs about 2 metric tons. So about the same as one of these kind of ginormous American pickup trucks. And here Euclid is being loaded into the launch vehicle. What about the instruments themselves? So this is the primary mirror. Again, this is 1.2 meter diameter, so about half the size of Hubble, and there's a hole in the center. So the way this works is we have the primary mirror, we have a secondary mirror suspended over the primary that reflects the light down through the center of the mirror into the science payload, which lies at the bottom of the telescope. So this is what the science payload looks like. So we're at the bottom of the telescope, and that's the main tube there. We have 2 instruments, which I'll talk about soon. So here's one of them, and then here's the other. So this is a diagram of how the light enters the 2 primary science instruments. So the light enters through the center of the telescope, gets bounced around a few times, and then it hits this dichroic here. And the dichroic splits the light, so it'll enter the 2 primary science instruments in Euclid, or science instruments in Euclid. So the first of these is VIS, which is our visible instrument, and then NISP, which is our near-infrared spectrometer and photometer. This is our near-infrared instrument. So VIS is basically a single broad-pass photometric band in the visible part of the spectrum, and we're going to use this to make those really precise shape measurements to do weak lensing. VIS was built at University College London's Mullard Space Science Laboratory in the southeast of England. And then NISP was built in Marseille with JPL contributions. So meanwhile, NISP is our near-infrared instrument, which comes with both photometric and spectroscopic capabilities. So we have 3 photometric bands in the near-infrared and grisms to do spectroscopy as well, to build up our spectroscopic clustering sample. Okay, what about the capabilities of these instruments? So here on the right, I'm showing the VIS instrument. So there's the CCD array. You can see what one of these CCDs look like if you just look at the bottom of the image here. In our nominal survey, we're going to go incredibly deep, down to an AB magnitude of 24.5. And then VIS just has one really broad photometric band between 550 and 990 nanometers. So in VIS, our pixel size are about 0.1 arcsecond on a side per pixel. So this is pretty comparable to Hubble, but the main difference is we've just got this enormous field of view of about half the square degree. And what that means is that we're going to be able to cover approximately the same area that Hubble has covered in its entire, I guess now about approximately 25-year lifetime, in just 5 or 6 days. So Euclid really is a survey instrument. Okay, what about the NISP instrument? So again, when we're imaging in photometric mode, we go down to an AB magnitude of 24.5. When we're taking spectroscopic data, we don't go quite as deep. So we go down to 19.5. We have 3 photometric bands in the near infrared, Y, J, and H. And then to cover the wavelength range, we have 2 different types of grisms in NISP. We have a blue grism and a red grism that go from about 900 to 1900 nanometers. And then the pixel sizes slightly larger in NISP, about 0.3 arcseconds per pixel. Okay, and now for the first time when I'm giving one of these Euclid overview talks, I'm really excited to actually show what the data looks like. So these are some commissioning images. This is from the VIS instrument. This is approximately a 10-minute exposure. And then on the left here, I'm showing the image across the entire focal plane. And then I've zoomed in on the right here, just inside this white square that's shown here on the left. And you can see a number of features in this image. So we've got a local galaxy here, local spiral. We've got some stars. We've got what looks like a group, maybe a small cluster. And then we've got these streaks, and these are cosmic rays. And I think the really nice thing about these images, I'd really encourage you all to go to the ESA website where you can actually look at these images yourself. The first thing to notice is just how small the PSF is, because we're in space. This means we're going to be able to do really precise weak lensing shape measurements, but they're also just incredibly deep. So I really would encourage everyone to go on the website and just zoom in. It's just absolutely stunning how many galaxies we have in each of these frames. And this just kind of gives you a comparison with the ground. So what I'm showing here on the left, this is the same field as on the right, except this is from the DESI Legacy Imaging Survey. And you can see that you can just resolve a lot more galaxies in Euclid. That's going to be really important for our shape measurements. Okay, and then this is data from NISP, from our near-infrared instrument. This is a Y-band image with 100-second exposure. So what I'm showing you here on the left, again, is the entire focal plane. And then I zoom in here on just the white square, and that shows the image there on the right. So just like Viz, they're incredibly deep with incredibly small PSF, excellent imaging quality. And then finally, this is the GRISM data. Again, this is from 100-second exposure, and then the GRISM disperses the light vertically, so we can read off the spectrum for all of these sources. In Euclid, we're expecting with GRISM to build up a spectroscopic clustering sample of about 35 million H-alpha emitters in the range just a little bit below a redshift of 1 all the way up to a redshift of 2. And that's going to allow us to do our spectroscopic clustering science. Okay, so what are our plans for the survey over the next couple of years? So nominally, Euclid is going to be a 6-year mission. There's a possibility that this could be extended, really depending on the availability of fuel. And the survey strategy, unlike LSST, which goes wide then deep, in Euclid, we're going to go deep and then wide. We're going to cover about 15,000 square degrees in the wide survey. So this is essentially the entire extragalactic sky once you cut out the galactic and ecliptic planes. So like I said earlier, in the spectroscopic sample, we're expecting about 35 million H-alpha emitters between a redshift of about 1 and 2. And then on the photometric side, we're expecting an effective number density of about 30 galaxies per arc minute. So these are kind of comparable numbers to LSST. And then compared to DES, we've got about 3 times the area and 3 times the number of galaxies. So in addition to that wide field survey, Euclid is also going to have 3 deep drilling fields. So this is going to be a great legacy science data set, but it's also going to help us calibrate those wide fields. As far as the public releases go, if you're not inside the Euclid Consortium, we anticipate 3 major data releases covering the first year of data, the 3rd year of data, and the 6th year of data. You can expect these about a year after the data is acquired. So we can expect the first year of data to be released after 2 years of the nominal survey. So if we start kind of towards the end of this year, you can expect that public data release towards the end of 2025. And okay, so this just shows the timeline again. So July 1st launch. We're still in the commissioning and performance verification phase, but nominally we expect to start the survey later this year. And what about the survey strategy itself? So like I said earlier, Euclid is going to go deep and then wide. So in the first year, we start at the northern and southern galactic caps. The idea is that for each individual patch of the sky, we're going to dither the instrument a few times, and then we'll never return to that patch of the sky again. And as we go through the survey, we're going to build up our area, starting at the galactic caps, and then building towards, and then eventually jumping over that ecliptic plane. So in addition to the wide survey, we have our 3 deep fields, EDF South, so that stands for Euclid Deep Field South, EDF Fornax, and EDF North. And these are chosen to overlap with some other interesting fields. And the survey strategy here is basically to linearly build up the depth over time. So when we're halfway through the survey, we'll have observed those fields for approximately half the time. And I should say we're expecting about 2,500 square degrees in the wide survey per year. And this is our wavelength coverage. So again, in the VIS instrument, we have one really broad photometric band covering a large part of the visible part of the spectrum to do our shape measurements. And then we have three photometric bands in the near infrared, in NISP, and these are Y, J, and H. And then when we're doing spectroscopic measurements, we have two different types of grisms. We have a blue grism and a red grism that cover the near infrared. Okay, so what about the science itself? So the first thing to say is Euclid, we have a consortium which is tasked by ESA to analyze the raw data and turn that into cosmological constraints. The last time I checked this morning, we have 2,797 members spread primarily across Europe, North America, and Japan. And in addition to kind of our key science areas of galaxy clustering and weak lensing, we have a huge number of other science working groups, which in the Euclid lingo we refer to as SWIGs, and task force, which in the Euclid lingo we refer to as ISTs, or Inter-Science Task Force, which are going to both build up our expertise to do those cosmological measurements, but also a lot of kind of general astrophysics, and even closer to home, things in our solar system. I wanted to highlight a few of these. So first of all, we have the IST likelihood, and this group is building a pipeline to turn those high-level data products like power spectra and correlation functions into cosmological parameter constraints. So we're building our own likelihood pipeline called Chloe, and this will soon be made available to the public. We also have a nonlinear task force, and this group is building all the models we'll need to extract information from small scales. So they're working on things like baryonic feedback models, intrinsic alignments, nonlinear RSD, and nonlinear clustering. And then we've got quite a few other working groups working in cosmology. So we have galaxy clusters, CMB cross correlations. We also have a very active theory group. And then we also have a ton of science working groups that are trying to do other science beyond cosmology. So I'll just leave these slides. And if you are interested in any of these, you can contract the science working group coordinators listed here. Okay, so Euclid is primarily built as a dark energy machine. So these are our forecasts from the Euclid Consortium's forecasting project for W0 and WA. So in purple, I'm showing our constraints from spectroscopic clustering. So these are full shape constraints. So that includes BAO, Alcock-Paczynski, and RSD information. And then in blue, I'm showing the weak lensing constraints, but the real power of Euclid really comes from combining all these probes. So in yellow, I'm showing the constraints from 3x2 point photometric statistics, so weak lensing, galaxy lensing, and galaxy clustering, plus spectroscopic clustering. And you can see that we get, or we expect to get, incredibly tight constraints on W0 and WA. It really is worth emphasizing that, to make these forecasts, we had to make a large number of assumptions. So, for example, we assume a Gaussian covariance, we choose certain scale cuts, and of course, we have to assume certain models for that nonlinear structure growth. So if you want to find out exactly what we did, I will refer you to this official forecasting paper. And then, of course, Euclid is going to expect incredibly tight constraints on sigma 8 as well. And perhaps over the next decade, this is going to help us resolve the S8 tension as well. Okay, so it's our ambition in the consortium to go beyond the traditional 2-point statistics. So I just want to highlight two projects in particular. So one of these is the HALS project, so higher order weak lensing statistics. And so recently, Virginia Anjani has led a forecasting paper to see what kind of constraints we can expect from a bunch of different non-Gaussian estimators for the weak lensing sample. So here we have the typical 2-point correlation function. So what I'm showing here is the covariance between all these different estimators. We have PDFs, Minkowski functionals, peaks, scattering transforms, and a few other statistics as well. And we actually calculated what constraints we can expect and which of these higher order statistics are the most covariant. So we can select the statistics which are most promising going forward. And then kind of my main contribution to Euclid in the last couple of years has been developing this new technique called K-cut cosmic shear. And the idea here is really to get really tight constraints in the face of baryonic modeling uncertainty. So the idea is that rather taking an L cut in our 2-point statistics, we take a cut directly in K through a linear reweighting of the data. So what I'm showing here is constraints on the dark energy figure of merit, so the size of those W0 WA contours for different lensing cuts and galaxy clustering cuts. And what we found is that with this new technique, we really can get a significantly higher figure of merit while still remaining robust to baryonic modeling uncertainties. So if you want to find out more about that, you can have a look at the official forecasting paper here. Okay, so Euclid also comes with a unique set of capabilities and also challenges. A lot of these really stem from the fact that we're in space. So the first advantage of Euclid is because we're in space, we're not tied to a particular hemisphere. So Euclid really is a cross-correlation machine. So in the north, we can cross-correlate with DESI to do galaxy-galaxy lensing measurements, also to calibrate our photometric redshifts. And then in the south, we can really imagine doing pixel level science in collaboration with LSST, which will make the weak lensing measurements in both surveys better. And we can also cross-correlate with the CMB lensing experiments or data sets that are available in the southern hemisphere as well. So another advantage of being in space is just our imaging quality is fantastic. So of course, the original motivation here is to do really precise and accurate weak lensing shape measurements, but there's many other things you could imagine doing with this really small PSF as well. So what I'm showing here is some simulated images of the same strong lensing system. So DES is here on the left, LSST is here on the right, the center, and Euclid is off here to the right. And really what you can see, it's only in Euclid that we're able to resolve this strong lensing system. So there's tons of other science cases beyond weak lensing where this really small PSF is going to be a huge advantage. But being in space doesn't come without problems. So one of the main issues is that we're going to be absolutely bombarded with cosmic rays. So what I'm showing here is a simulated image, vis image. So this is for the end of life of the survey. So things are not quite as bad now. And these streaks that you see, these are cosmic rays hitting the detector. And then you see this kind of smearing from left to right. This is due to an effect called charge transfer inefficiency. And what's happening is that as you read the CCD from left to right, electrons are getting trapped and then smeared across the image. And as you can imagine, when you're trying to do really precise and accurate weak lensing shape measurements, this is a major issue. So Euclid has a very sophisticated pipeline, both to remove cosmic rays and also to account for the effects of CTI. And we really do need this. To be unbiased, we really do have to remove the overwhelming majority of these cosmic rays. Another major challenge for Euclid is to get really precise and accurate photometric redshift estimates. So nominally, our intention is to use about 10 tomographic bins with incredibly small photometric redshift uncertainty dispersions. So this is kind of the fiducial binning that we're using at the moment from one of my forecasting papers a few years ago. And this is really just going to be a major challenge for Euclid. So we have dedicated spectroscopic and photometric campaigns, ground-based campaigns, to help us calibrate our photometric redshift uncertainties. And I just want to highlight a few of these today. So the first of these is the C3R2 survey. So this used about 50 nights on Keck and obtains about 5,000 spectra. So what I'm showing you here is a projection of the color space in Euclid, so the full color space projected with a SOM down onto 2D. And then each of these pixels, so each of these pixels will contain, or expect it will contain, a number of galaxies in Euclid. And every pixel that is colored in, that means that we have at least one spectroscopic galaxy inside that pixel. And then the color just shows the median redshift of those spectroscopic galaxies. And then the white pixels, we don't have any spectroscopic follow-up. So what C3R2 did for us is it took our coverage from about 50% of these pixels to about 90% of these pixels. And because of the uneven number of galaxies in each side of these pixels, it means that we're expecting about 90% of our photometric galaxies to lie in one of these colored pixels where we actually have spectroscopic follow-up. And then Euclid also has a ground-based photometric campaign called Unions. So this survey will be obtained with data from CFHT, Pan-STARRS, and the Subaru telescope. And this will cover about 5,000 square degrees in the U, G, R, I, and Z band in the north. Okay, so you're probably wondering, there's one last challenge, and that's unlike DESI or the other ground-based spectroscopic instruments, we're not using fiber spectroscopy. We're using grism spectroscopy. And as you can imagine, because this image is kind of an absolute mess, right? We're dispersing the light for all the galaxies along this direction. We have 3 red grisms that are at different angles, and then a very sophisticated pipeline, which is going to help us disentangle this kind of just what looks like a total mess to the naked eye, and help us build up that spectroscopic clustering sample of about 35 million galaxies. Okay, so you're probably wondering how you get your hands on the data, particularly if you're not in the consortium. So NASA, this is really focused at the US audience, but NASA has established the Euclid NASA Science Center at IPAC, which has a nice acronym NSCI with I guess 2 other acronyms inside of it. The website can be found here, and you can contact the help desk here. And NSCI has been set up to support the Euclid science community in the US. So it'll provide tutorials, updates and documentation, as well as act as the archival node for Euclid data in the US. Again, as far as our data releases go, we're expecting our first data release DR1 in 2025. We'll have petabyte scale data products. So in the first year of data, you can expect images, mosaics, spectra, photometry, line fluxes, photometric redshift catalogs, as well as high-level data products, so like correlation functions, power spectra, and covariance matrices. It is really important to say that if you have a particular science case and you're concerned that the data won't be available inside the data release, that you can contact NSCI with this information here, just to make sure that the data products that you need will be made publicly available. It is also worth saying that we will have a quick data release after about 14 months of observation. So this will just cover about 50 square degrees and just give the community a chance to start working with Euclid data before the first data release anticipated towards the end of 2025. Another really important point is NASA is involved with Euclid and will support research with public Euclid data. And this can be funded through the NASA's ADAP program. So I think with that, I will leave it there and open it up to questions. And thanks very much for listening.
Thank you very much, to Peter. You have, clapping hands coming in from the chat. So you have actually quite a few questions. Some of them you may have already touched on, but I'll go in the order they appeared. So like back up to the beginning of your presentation.
Okay.
Okay, so the first one says, what are the differences between Euclid and Nancy Grace Roman telescope?
Right, so Nancy Grace Roman is slightly further into the infrared for the imaging. So for example, an advantage of that is that we don't have CTI when we're doing our weak lensing shape measurements. Nancy Roman, I mean, I guess the survey hasn't been finalized, but nominally it'll be deeper over a smaller area. So Euclid covers 15,000 square degrees, and then Roman will be likely a much smaller survey in the south.
Okay. And then I heard you mention CGI, so I'll skip to the following question on this, which is from Mandeep Gill, that says, it looks great so far. What are those advanced techniques to correct for the cumulative effects of CTI over time versus just removing individual cosmics? And then there's a follow-up that says, and have you already started to see the initial effects in commissioning from CTI and correct for them?
Okay, so I'm not a CTI expert. I believe that details about our CTI pipeline are in one of our Euclid papers on arXiv, and I don't want to talk about things I don't know about, so I'll just refer you to that paper. So these images here, this really is from the what we expect from the end of life. You can see that our actual commissioning data looks a lot better. So you can see a cosmic ray here, for example, and you don't see this really dramatic CTI. So these are not calibrated to do science. This is just the raw data, if you like, but the effects are not as bad as they will be at the end of the survey.
All right, thank you. Another question that is to do with the observing strategy. How many times will each point in the sky be hit? How long a period will this cover?
So I think, I don't know exactly, but it's like order 3 to 5, around that kind of number, how many times each patch will be hit.
Okay. Oops.
And I mean, the time period is you literally just dither the telescope and then you move on and you never come back to that point in the sky again.
Okay. I'll go in order. Next question is, I know Euclid will detect 10 to the 5 clusters, but could you please tell how will be the redshift distributions? At what wavelength will Euclid see those clusters? I know we will be able to calculate mass from the scaling relation from that signal. Is that true? Can we probe the mass of those clusters using the weak lensing from Euclid? Also, can we calculate the mass cross-correlating CMB lensing as well? Sorry for such a long question. Thank you.
Well, I think the answer to all of those questions at the end is yes. I don't know the exact redshift distribution. There is a cluster working group. I don't know if they've made any forecasts available to the public, but if you want to find out more about the cluster science, then you can contact the cluster working group leads, which are listed here. And I hope they can answer your questions, and sorry that I can't.
Okay. Right. So this is a question regarding your data release, anonymous question, and for non-US scientists. regarding the data release, so for example, year 1, are calibrated shape measurements included for non-US scientists? Do you know?
Yeah, so NSI is the Euclid node. Sorry, the US node. ESA will also support data release. Whether or not the calibrated shape measurements are released, I'm not sure exactly what will be released. I assume they would, but if you're really concerned about this, you can either contact NSI and just ask that question, or the European Space Agency's help desk, which is listed somewhere on the Euclid website.
So is that fair to understand that NSI and ESO, they each, cater to different continents, but they will, however, share the exact same data products, or could we expect some differences between the two?
So ESA will support the entire public data release, and then it's to be determined. So NSI will support either a fraction or the entire data set. That's, I think, still to be decided.
Okay, thank you for those clarifications. Next question is, what is exactly the strategy for PhotoZs? Will you use ground-based photometry whenever possible?
The strategy is just to use everything that we have available. So we have access to all the, the public data that exists now. And then we also have these kind of dedicated follow-up campaigns. And I think it really is still to be determined what the optimal strategy is. And of course, we also have access to all the public spectroscopic data releases as well.
Okay. I see hands pop up in the attendees. It would be better if you could post your question in the Q&A so we can ask it there rather than ask you to unmute. Next question is, do you have examples or references to how the GRISM data correction looks like?
Yeah, so I think there again, you can go on the ESA website. There is a list of all the Euclid papers. Sorry, on the Euclid Consortium website. So if you go there, you should be able to find at least all the publicly released information about all the pipelines in Euclid. And now we're also starting to ramp up now that data is coming in, and you can expect a lot of papers to be released in the next year as well, talking about the ground segment, which is responsible for this pipeline.
Okay, and we'll see about copy pasting that link in the chat for easier access. Next question is from Bruno Moraes. Thanks for the great talk. After a few years of having made this choice, what is the current assessment on the advantages and disadvantages of not having multiple photometric bands from space to do the PhotoZ measurements?
Well, I mean, more bands would always have been great, but I mean, building, an instrument and putting it in space is a incredibly difficult task, and we have what we have, and we also have ground-based follow-up to calibrate our photometric redshifts. But more bands would have always been good.
You mentioned the ground-based follow-up. So about the disunion survey, it went a little fast. Could you go back to what are the advantages and particularities specifically of that survey, and what is this expected to be public? What does it bring compared to other surveys of the same areas and all of that?
I don't know about the publication date. I mean, the main advantage is, I mean, we have DES in the south and LSST, but unions is in the north, and we're covering a lot of these optical bands, so UGR, I, and Z, and it's over about 5,000 square degrees, so it really is quite a wide survey. I guess one of the kind of peculiarities is we're not just taking this data on one telescope. So we have CFHT, Pan-STARRS, and then this WISHES survey is on Subaru.
Okay. There's someone who's asking for Sigurd is asking for precision about the first light image on the Euclid website that you mentioned. So he went to, euclidec.org and just Euclid sees first light, and is asking if it's the same image that you've shown in your talk, or is there a fuller resolution one available somewhere else that he hasn't found?
So it may or may not be the same image that's in my talk. I took this slide from another Euclid talk, but as far as I'm aware, the public release images are on that website. I don't know if there's better resolution images available elsewhere. Sorry.
Okay. I do not see any other question at the moment. So what I'm gonna suggest is if you can stick around for maybe 5-10 minutes, I'll see if we have more questions, and we can post the relevant links in the chat for now. And if people feel they don't want to ask questions, but while the webinar was fully going on, we can have also answers then in the chat instead. And again, Peter, thank you so very much for representing the Euclid collaboration. Thank you for a great talk. And if for the attendees, we'll reconvene at the half-hour mark, so nearly in 40 minutes, 50 minutes, for an update from Shoes. And the recordings, answer to the question, slides will be available on the website. So thank you all so much.